So hello, today we'll be discussing something about Alien's trick, which is also known as Lagrange's relaxation. Okay, so it involves a little bit of math related to convex functions and stuff. We would be skipping that part. Our main goal today would be using the technique to solve some good amount of problems. So I've also picked some problems. For some problems the Alien's trick is an overkill, like this one. Okay, but still we'll be doing it just for the purpose of learning it. We just want to learn stuff, even if it's an overkill. So the basic idea is, in some DPs you might have seen questions like you need to pick exactly k items, or you need to pick at most k items. Okay, so you need to pick exactly k items or at most k items. So in these cases, what is the common idea is, inside the recursion you maintain a count dimension. Inside the recursion you maintain a count dimension. You would have some constraints. You would maintain the count dimension, and after writing some sort of a base case like some I equal to n, right? Okay, I just took a random base case. This always won't be the base case, but when I equal to some random base case, if let's say this is the base case, and if count is less than or equal to k, then you would return something valid, else you would return something as invalid. If your count is less than or equal to k, then the DP construction is valid, otherwise it's invalid. Yeah, so in this case you would prune it. Like if you are maximizing something, you would return a minus infinity here and you would return a 0 here. That's how you would be handling this. Okay, so that's one way of doing it. The other way, which is used in the Alien's trick, let's say there are some n items. There are 2 items, and I want you to buy only one item. I want you to take only one item by paying the price of one item. I want you to take only one item, and I want to restrict you from buying the second item. Your budget is 10, let's say. What should I do in order to restrict you to buy one item only? One way would be the DP dimension which I have discussed. I would maintain the count of item which you have bought, and if it's exceeding k, then I would prune that possibility. I won't let you buy that item. Okay, I won't let you buy more than k items. But there's also another way, which is, what if on buying I say that you can buy all the items, whatever the items are there. I don't restrict you. You can buy all the items, you can buy whatever you want, but every time you buy some item, you have to pay some penalty. Lambda. Okay, every time you buy an item, you would have to pay a penalty lambda. Okay, so you might be like, okay, that's fine, but using this, how did I restrict you to buy only one item? So let's say, if you buy the first item, and I say, the moment you buy one item, you have to pay me the penalty $5. Okay, the moment you buy one item, for every item you need to pay me the penalty 5. What would happen? Your budget is 10. You would buy the first item. Now your budget is 5. And I'm asking you for a penalty of 5. And you would pay me this 5 here. Now your budget is 0. With this, I restricted you from buying 2 items. I restricted you to buy only one item. Okay, so with this, I restricted you to buy only one item. But is it needed that the penalty should be 5 only? Can it be lesser? And can I still restrict you? Can I still restrict you even if it's lesser? Yes, I can restrict you even if it's lesser. What would happen if penalty is 4? If penalty is 4, you would be left with budget 1. You cannot buy this yet. Okay, even if I just put penalty as 1, since your budget is strictly 10, you would be left with 4, and with 4 you can't buy an item with price 5, right? So the minimum penalty to restrict you to buy k items only is lambda equal to 1. Lambda equal to 1 is the minimum penalty which I would have to impose so that you would buy only one item. And now what's your total expenditure? You have bought, let's say I want to know the price you are paying, like what's your total expenditure, actual expenditure without penalties. Penalty is something which we are adding as a substitute for this DP. We are adding penalty as a substitute for this DP, some extra dimensions and k. You are adding penalty as a substitute for this DP. Instead of maintaining the count dimension or k, instead of maintaining the count dimension, you are adding the penalty. So the penalty is a substitution for this DP. To remove this particular state variable, to reduce the state, you are adding this penalty. That means if this DP gives the optimal answer as 5, which is true, you have paid 5 and the next item you can't buy because k is equal to 1 only. This particular idea should also give you the profit 5. But using this idea, I am taking an extra penalty, 5 plus lambda, which is nothing but 5 plus 1, which is equal to 6. The total price you are paying is 6. And to recover from this price, like I want to produce 5 again. To recover, I need to, if I am let's say adding this lambda k times, I would obviously add this lambda k times only. So if I am adding this lambda k times, I would have to remove it k times as well. Okay. To recover from this, I would have to remove this k times as well. And this particular value would always remain k. That's the magic. Always remember, do not write, do not count how many times you are removing lambda and remove the same amount of times. That won't work. Because inside this particular process, we are finding the most minimum lambda. We are finding the most minimum lambda. We are not finding any random lambda. We are finding the most minimum lambda. So always it would be 5 minus k lambda. K would be the number of max items which you can pick. Okay. This would always be k only. Do not write count here. That's the important tip. Note it down somewhere that, okay, it is blindly always k. Don't try to by heart these things. Some part of it is a black box because we don't know lots of math behind it. It is always k. Why? The reasoning for this is binary search. So how would I find some optimal lambda? Is that, let's say again the same example, 5, budget equal to 10, and I want you to restrict to buy only one item. What I would do is, I want to find some lambda, so that using this lambda as penalty, I restrict you to buy only one item. So what I would do is, or else perhaps let's take it as at most k items. So let's say with some lambda mid, you are able to buy 10 items. That means I should increase the lambda. You are able to buy more amount of items than what is required. That means I should increase the lambda. I should increase the penalty so that I force you to buy lesser items. So I would do start equal to mid plus 1. And it's monotonic basically. What I'm trying to say, it's monotonic. Okay. If With 5 you can buy less than or equal to k items. With 1 also, with 1 you can buy less than or equal to k items, and 5 equal to, sorry, with 5 also you are able to buy less than or equal to k items. Anything in between would give you true. Can you buy less than or equal to k items? True. Can you buy less than or equal to k items? True. True and true. This is what would happen, and after 5 it would be false. Okay, that's the core thing. Or else perhaps less than this thing it would be false. Sorry, my bad. Less than this it would be all the way false. Okay, so that's the idea. Using binary search we are finding the minimum most lambda, and minimum most lambda would always have the upper bound to be multiplied as k. It would be to recover the profit back, to recover this 5 back, I need to remove this k times. So understand this much. Now let's jump into the problem directly. So the problem says you are given an integer array prices where prices of I is the price of a given stock on ith day and an integer k. Find the maximum profit you can achieve. You may complete at most k transactions. You may buy at most k times and sell at most k times. You may not engage in multiple transactions simultaneously. You must sell the stock before you buy again. Okay, so that was the problem statement, and the problem statement restricts you to do only k transactions. So this gives you a vibe of Alien's trick. So let's say there's some ith day and currently I'm holding some stock or not holding some stock. So it would be true or false. If it's if I have already bought something, I would have to sell it first to buy something again. If something is previously on hold, it should be sold first, then only the next item should be bought. Okay, then only the next item should be bought. And now I have the count dimension. So if I equal to n, that means I am on the very last day, all the days have completed, and I have done less than or equal to k transactions. I have done less than or equal to k transactions. That means this construction is valid, otherwise it is invalid. Since I am finding the maximum profit, to prove it I would return negative infinity. So constant infinity equal to 1e9 and minus infinity would be here. This would be the normal DP. This is not the Alien's trick which I am writing now. And if I am holding something, I should sell it first. So I need to return maximum of recursion of, I would move to the i+1 day by skipping it. So I am still holding the stock, waiting for a better profit, or else I am selling it. So I am going to the i+1th day, and now I am not holding the stock anymore. And if I am not holding the stock, I would return maximum of, either I can choose to skip the current item, or buy this one. And if I am buying this one, this would become true. And when I am buying, I would have to pay the prices of I. Here when I am selling something, I would receive the prices of I. This would be the recursion. And yeah, also one more thing, here the count would remain as it is. The moment I sell, I am completing a transaction. A buy to sell cycle is a transaction. I am completing one sell, so it's a count plus 1. Here it is count as it is. Here it is count as it is. Fine. This would be the naive recursive solution. Let's see if this passes. Deeping this wouldn't be hard, I believe. If you are watching this particular video, I don't even think writing this DP is a big thing for you. n equal to prices dot size, and this prices is equal to prices, this k is equal to k. We need k also, by the way. Zero, and initially I am not holding any stock, and initially the count of stocks I have picked is, sorry, the count of transactions is 0. Runtime error. Stack overflow. I guess we should be deeping this. Or else let's add something like if count greater than k, return minus infinity. Would that help in any way? Still it's a runtime error. Are we doing it right? Let's try to DP this once. Or did we mess up something? We forgot the return statement. That's what I was thinking. Because the first few test cases are pretty small. It shouldn't be giving Stack Overflow. Yeah, so the recursion is right. Now all we need to do is convert this into alien string, and I would be telling you a very powerful template. What was the question number? I'll be telling a very powerful template. So let's understand the template. Once the template is clear, it's very easy stuff. Then we have pasted the recursion, naive recursion 1. Now the thing is, comment this first. Using this recursion we would be writing the alien string recursion. So first thing we would need a struct node. Inside this node, what do we need is, for every lambda, what should I do? If I have a particular lambda, I would require with this lambda how many items I am able to pick, the count of items. How many items am I able to pick with this lambda? And with this lambda, what is the max profit which I am getting? Max net profit. Net profit in the sense, it would be profit, actual profit, plus some x times of lambda, or else, yeah, since we are maximizing, it should be negative. Okay, since we are maximizing stuff, if you are adding a negative penalty, the max function would not pick it. Okay, we want to let max function do the thing, and max function would not pick it if it goes too much negative. So some x into lambda. This would be the net profit. Okay, we are storing these two things. So I would have to store int profit and int count. Okay, these are the two things which I have to store in the node, and I would have to write node recursion. Using this optimization, which dimension are we trying to eliminate? We are always trying to eliminate the count dimension. This optimization is mainly meant for eliminating the count dimension. So the remaining dimensions would remain as it is. And if now this has become unbounded stuff, this has become an unbounded knapsack. Previously it was a bounded knapsack. You had a bound of picking only k items. So this particular optimization converts this into an unbounded knapsack. You can pick as many items as you want. So if this is equal to n, return 0 0. You cannot pick more items after this. So return 0 0, and if holding is true, we got two choices. One is node skip. If you skip, it would be recursion of I plus 1. Holding would be as it is, you won't be selling it. Next thing is the sell. If you sell it, you're not holding it anymore, so this would become false. You're not holding it anymore, it's becoming false. And when you're selling it, the profit that is getting added to the net profit is it is prices of I. The profit that is getting added to the net profit is prices of I, and the count that is getting added to this is 1. And to this profit, the penalty that is getting removed is the penalty that is getting subtracted is some penalty. Let's say it is some penalty. And if you're not holding anything, still we got two choices, which is recursion of I plus 1 holding, and other choices buy. If you're buying something and if you're not holding something previously, this would become true. And when you're buying something, from this profit you should subtract the prices of I, and sorry, this is buy, right? Buy profit minus equal to prices of I. Okay, this particular price is getting subtracted, and we will be removing the penalty, like subtracting the penalty, only when count is getting incremented. Otherwise we are basically restricting the transactions, right? So for every transaction, every completion of transactions, you need to add a penalty. So yeah, buy dot profit, here we won't be doing anything with the penalty as well as the count. So buy dot profit minus equal to price of I, nothing else is changing. Now we need to check which among the given choices is better. So to do that, we would be writing a small function which is node better. Okay, const node ampersand a, and const node ampersand b. So when can you say that a particular node is better? When its profit is higher, when its A's profit is higher than B's profit, A is a better node, otherwise B is a better node. What if profits are equal? If both are giving the same profits, then what would happen? Let's say it would depend on the count. Obviously we have only two things to compare, one is profit, other is count. So let's say one of them is giving the profit 10 in 2 transactions, one of them is giving profit 10 is 6 transactions. Which is better? If I'm taking the one with 6 transactions and my k is equal to 5, this particular thing would get pruned. Obviously this particular thing would get pruned because k is only 5. If I'm considering this, I'm getting something with the 10 profit and it's not getting pruned also, so it's always better to take the one with the lesser count. So if a dot count is less than b dot count, then a, otherwise b. So this would be the better one. We have written the better function and we need to return better of both, better of skip and sell, and here also better of skip and buy, skip and sell and skip and buy. Okay. So this was about the recursion. Now all we need to do is finding the optimal lambda. So let's say some answer is equal to infinity is the best lambda. This is the best lambda. We don't know it yet. So what's the definition of a best lambda? So here I need to find, and it's almost all the time, I need to find the most minimum lambda that lets me buy at most k items. Okay, first thing, I want to give this liberty. Okay, if something has to do with k transactions, or I want to pick some k items, I want to give it complete liberty to buy pick exactly k items. I would give it complete liberty to buy or pick exactly k items, but I won't let it buy more than k items. Okay, so if I want this to buy as many as items as possible but not exceeding k, I need to find the most minimum lambda. I need to find the most minimum lambda that would help me pick less than or equal to k items, isn't it? I should find the most minimum lambda. I should find the most minimum lambda. Why? Because I don't want to restrict it to less than k transactions. If there's a chance, I would surely give it the liberty to take k items, but not more than k items. I would stop it here, not anywhere in between. So I want the lambda to be as minimum as possible, as well as it should restrict from transactions being higher than k. So using a binary search, I would do this. How? If this is the penalty, mid is the penalty, with mid the current recursion is being called recursion of 0 0, this is being called, and if current recursion the max profits count is less than or equal to k, this particular penalty could potentially be an answer. This particular penalty can potentially be an answer, but what am I trying to do? It's picking less than or equal to k, but I want to make it pick like as much as k. I want it to be as close as to k. Okay, so if my k is 5, I should make sure that I'm not forcing it to pick only 4 items. I would give it complete liberty to pick till 5 items. So what I should do, I should decrease the lambda so that it gets a little more liberty to pick more amount of items. So I would do end equal to mid minus 1. I would decrease the lambda, and else I would do start equal to mid plus 1. Else in the sense current dot count is greater than k. If it's greater than k, I should increase the lambda so that it picks less than or equal to k items. Okay, this is the complete idea of binary search. And since I am always making it the minimum penalty, like the minimum penalty I should be adding while recovering the profit, I need to do okay, now I have the best lambda, which is nothing but the answer. So I would do once penalty equal to answer, and with this best lambda I would do the best profit. So the best profit would be with this lambda, and after finding this best profit I would return best dot profit. Now I have to recover the profit, and as I told you, it is always k. Why? The binary search finds one such lambda such that on multiplying this penalty with this best penalty with k, it would recover the profit. Why? Because we are finding the minimum penalty. We are giving liberty as much as the range. See, understand this thing. Okay, I'll give clarity on this thing also, because it's not very intuitive for too many people. So the thing is, let's say, what did I tell you? If my k is something, I should give freedom till k. I should give complete freedom till k. The recursion should be able to pick at most k items. It should pick k items also. So the lambda would be such a way that the penalty would be in such a way that it allows you to pick k items. It allows you to pick k items. But what if the recursion picks only 2 items? What if the recursion only picks, I gave it liberty to pick k items, but what if the recursion pick only 2 items? If I do this, because I found the lambda for k items, if I do this, the recursion picks only 2 items. If I do profit plus 2 into lambda, would that be right? It would be wrong. This would be wrong. I gave it liberty to pick till k items, so the lambda is according to this k. The lambda is according to this k. So this should not be 2 items just because I've picked 2 items. This should be k lambda. This should be k lambda. And I know the fact that in the optimal recursion, which is picking 2 items, the lambda is getting removed only 2 times. But coming to this lambda should be added k times only, because I gave it the liberty to pick k items at most. I gave it the liberty to do k transactions at most. So remember, it's always k. It's not this. It's not this. Okay. This is very problematic statement. That okay. So every time count number of times the penalty gets removed, I would add the penalty count number of times to recover the profit back. No, this is a problematic statement. The penalty is tuned in such a way that on adding k lambda, you recover the profit back. So don't do this. It is always k lambda, and best lambda is the answer. So this is the answer. Okay, I shouldn't have used int penalty here. Fine. Here also it shouldn't be int penalty, and rather the penalty should be a global variable, which is here. So yeah, this would be the solution using the aliens trick, but this is naive recursion. We would be dping this. So let's dp this here itself. Okay, so I would take a vector node dp, and before calling the recursion every time, everything is a fresh recursion, so I would do dp dot assign n+1 and vector node. Initially, what would be the value of this? Okay, so initially what would be the value of this vector node, and we have dimensions. Holding is either true or false, so this is true, sorry, 2, and let's say I assign this with infinity comma 0. Fine. And before the final recursion also, or else if you are having the confusion with initial values, what is the other thing you can do is keep it this way only. Maintain some other visited array. Okay, maintain some other visited array. That's better. Whenever you are having confusion with what should be the initial value, maintain a visited array. So now the dp doesn't matter. The dp array doesn't matter. Visited dot assign. We would maintain whether this particular state is visited or not. Vector int 2, and the same things here also before calling this recursion also. Where is it? Here. Okay, so if you are having problem with the visited values, initially visited would be nothing is visited. okay, nothing is visited initially. Nothing is visited initially, and using this visited array you can check the DP cases, like if it's a visited state, if visited of I and holding, then return DP of I and holding and visit this state. If not, since you have started computing this state, visit this state. This is equal to 1. And done. Let's try to run this one. Hopefully it should run in the first try itself. Wrong answer. What's wrong with this? First one works, second one, what's wrong with this? Did we do something wrong here? Is there anything wrong here? This is return 0 0, fine. Visited is visited, shouldn't be a problem. So did we take answer? Yes, we have taken answer. DP assigning is right. Best dot profit plus this thing, even this is right. Oh yeah, we forgot, we are not doing DP. Sorry, my bad. That was weird. My brain suddenly didn't understand the code properly. I forgot to do this. Okay, now this should work. Yeah, done. So using this aliens trick we have eliminated the, okay, we haven't done anything. Output is this thing. Output should be 6. Are we taking the profit as too small? Sorry, the infinity value as too small? Not really, 189 is fine. We don't need anything else, LL type stuff also. If I take answer equal to 0, that also wouldn't impact anything much. Let's use this test case. Prices, k, answer, start. Okay, end is infinity. Done. That was another mistake. Did I really write this? End equal to infinity. End should be infinity. Done. So this was the aliens trick for this problem. Okay, and this is a strict template which I follow. It's always a struct node. It's always a struct node with count. It's always a node better. It's always a recursive function and it's always a binary search where I do all this stuff, and this is called WQS binary search as well. Okay, so I guess I should be skipping this problem and leaving it to you. Okay, I'd be rather telling the okay, so it has a journey for me for this problem. Accepted. Let's take the first time limit exceeded. I guess it would be the naive approach. The first time limit exceeded. Yeah. So let's first read the problem. Your task is to partition nums into exactly k subarrays. Once again, it's a counting one. You would maintain how many parts you have done so far. So it's once again a counting one, and return the integer denoting the minimum possible score among all valid partitions. The score of a partition is the sum of the values. The score of a partition is the sum of the values of all its subarrays. Okay, the score of a partition is the sum of the values of all its subarrays. So when you're partitioning something like this, the question says that the sum of this and the sum of this would be the score. So if I'm making a partition till like this, some partitions, it's nothing but the prefix sum of this. It's nothing but the prefix sum of this, 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 and this, which is getting added to the score. It's a basic observation. Okay, so if parts is equal to 1, return cost of n minus 1i. That means if there's a single part, you would return the complete prefix sum, cost of n minus 1i. And if this is a DP check, answer equal to infinity, because we are minimizing the cost, and we need to pick some optimal j starting from I. So till I it's all parted, till I it's everything is parted, till some I it's parted. So let's take some j starting from here, pick whichever is the optimal partition. Okay, pick whichever is the optimal partition. From that j plus 1 index, the next partitions would start, and the remaining partitions would be parts minus 1. Okay, so once again it's a counting one. It once again is a counting problem. So this is the naive recursion for this, and I hope we can do the aliens trick for this to do parts counting. Okay, so this recursion can be converted into aliens trick for doing the parts counting. Okay, so I'll be skipping this and leaving this to you. And we have the next problem. This has a little taste of probability. So a small prerequisite I want you to know is the expected value formula. Expected value E of x is equal to sigma x into probability of x, where x is an event. The expected value of an event is x into probability of that event. Okay, expected value is x into probability, the actual value and its probability. Okay, so that's a prerequisite. That particular formula would be a prerequisite for this one. And let's see the duration once. 44 minutes, not bad. Okay, so let's read the problem. There's a person, Gosha, he's hunting. His goal is to catch as many Pokemons as possible. Gosha has A Pokeballs and B Ultra Balls. There are n Pokemons. They are numbered 1 through n. And Gosha knows that if he throws a Pokeball at the ith Pokemon, he catches it with a probability P of I. Okay, the probability of catching Pokemon, the probability of this event is P of I, If he throws an ultra ball at the ith Pokemon, he catches it with probability U of I. He can throw at most one ball of each type. He can throw at most one ball of each type at any Pokemon. The hunting proceeds as follows. At first, Gosha chooses no more than A Pokemons at which he will throw Pokeballs and no more than B Pokemons at which he will throw Ultra Balls. After that, he throws the chosen balls at the chosen Pokemon. If he throws both Ultra Ball and Pokeball at some Pokemon, he is caught if and only if he is caught by any of these balls. The outcome of a throw doesn't depend on the other throws. Gosha would like to know what is the expected number of Pokemons he can catch if he acts in an optimal way. In other words, he would like to know the maximum expected number of Pokemons he can catch. Okay, so that was the problem. Now this problem becomes interesting because so far we have seen the both problems which have only one counting dimension. In this particular problem we have two counting dimension. We have to maintain the count inside the recursion for both Pokeballs as well as Ultra Balls. Okay, so as you know what are Pokeballs and Ultra Balls. Those were the days I used to play Pokemon Fire Red, Leaf Green, Emerald, Ruby, etc. etc. Those were the good days. I still used to write some amount of code during those days. Okay, anyways. So that was the time I had started to write code already. Okay, so this time there are two counting dimensions. Forget about the alien trick. What was the first thing to approach the problem? We have to write the naive recursive approach before jumping to the alien trick. So should I use my template or it would lose the clarity? It would lose the clarity of the code. I guess I should not use my template. Let it be clear for someone who's watching. Okay, so let me do some basic stuff. These are the bare minimum things. Hash define ld long double, hash define int long long, hash define endl \n because I'm habituated to write endl, and let's take a signed main because we have done hash define int long long. Sync with stdio false, scene.i null pointer. Yeah, there would be no test cases. Okay, there would be no test cases. What is the first thing? It is n, a and b, so it's number of Pokemons. It is, let's take them outside, int n, a, b. Okay, and we have the probabilities given. The probability of catching ith Pokemon with a Pokeball, the probability of catching ith Pokemon with an Ultra Ball, right? I wish there were Master Balls. All the probabilities would have been 1. Yeah. I guess you people know Master Balls, don't you know? Okay. But there's also another case which is both Pokeball and Ultra Ball, which is both Pokeball and Ultra Ball, So we have this PA. Let's take it as probability with Pokeballs. So PA would be, or else they have given this array as P. So let's take it as P. P1, P2, so on. Pn. N goes till 2001. and U, which is the probability with ultra balls, which also goes till 2001. And let's take another probability, which is PU, both Pokeball and Ultra Ball, both Pokeball and Ultra Ball, and this would also go till 2001. So we are trying to like maintain this arrays as some sort of pre-compute, and anyways they are given, so it's obvious that it's a pre-compute. Yeah, it's not even a pre-compute, like it's already given data. We are maintaining it globally so that we can use it. Sorry, my bad, pre-compute was the wrong word. So for int I equal to 0, I less than n, I plus plus, okay, C in P of I. For int I equal to 0, I less than n, I plus plus, C in U of I, which is the probability with ultra ball. Now what should I do to find the probability with both Pokeball and ultra ball? What should I do? To find that particular probability, if you know the basic probability, it's enough, I guess. I guess you would understand this formula. The probability of both Pokeball and Ultra Ball is nothing but this. Probability of Pokeball and or Ultra Ball is equal to, let's call it some PU, 1 minus neither Pokeball nor Ultra Ball. 1 minus, so 1 is the total probability, okay, of a canon event, and if you remove if you exclude this particular probability, you would get the probability of both Pokeball and Ultra Ball. So let's take, by the way, these arrays should be of type long double, my bad, and long double neither Pokeball nor Ultra Ball is equal to 1 minus P of I multiplied by 1 minus U of I. This is neither Pokeball nor Ultra Ball, and Pu of I is equal to 1 minus neither Pokeball nor Ultra Ball. This would be the probability. Okay. Now we need to do the DP stuff. So I'll be writing LD recursion int. Do we need something else? Only DP, right? Yeah. I'll be taking some level or something I, and let's say some, initially we have Pokeballs equal to this Pokeballs count. Now we have two count dimensions. Let's see how to solve this. And int Ultra Balls. Ultra Balls are these many. Okay. So if at any point Pokeballs is greater than A, or Ultra Balls become greater than B, then return minus infinity, and minus infinity is not defined, so let's declare const int minus infinity is equal to 1e 18 maybe, sorry, constant infinity, and yeah, we'll return this. Now so if I equal to n, I'm habituated to writing this thing called level, which is which happened when I was learning. When I'm writing recursion, I usually think of it as a tree. So in this tree you are at level 0 and you have these few choices, okay, aggregates are the edge weights and you move to the next level, so it's level plus 1. That's how I think. So I'm habituated of writing this level thing. Yeah. Return Pokeballs if it's exactly A and this Ultra Balls consumed is exactly B. In that case, return 0, that means accept, otherwise prune. And now we have the choices. What's the first obvious choice? Skip the current Pokemon. Skip the current Pokemon. If you skip the current Pokemon, it would lead to recursion of I plus 1. Recursion of I plus 1. And you are not throwing any Pokeballs on it, so the Pokeballs count won't change. You are not throwing any Ultra Balls on it. Ultra Balls count also won't change. And the other way is throw a Pokeball, which would result in probability of I. What's the formula of expected value? Once again, probability into actual value. So you're throwing one Pokeball, so it's 1, so I'm not writing it, plus the remaining recursion would do its work of computing the remaining sum. The process of computing the remaining sum, it would be done by the recursion. I'm not writing that 1 here. I hope it's understandable. And recursion of I plus 1. This time you're throwing a Pokeball, so Pokeballs plus 1. And you're not throwing an Ultra Ball, so the Ultra Balls count won't change. The next possibility is throw an Ultra Ball. And if you throw an Ultra Ball, it would have the probability U of I. I'm not writing into 1 because it doesn't matter. And you're moving to the level I plus 1, then Pokeballs count won't change. Ultra Balls count would change. You have thrown an Ultra Ball, you have used an Ultra Ball. And the next thing is throw both, or let's call it both. When you're throwing both of them, the probability is PUI. And since it's an independent event, you need not write it as 2. It's an independent event, so even either of them would catch. It's an independent event, so it would still be 1. And recursion of I plus 1. If you're not understanding this, it's absolutely fine. Alien's trick is done. We are discussing the core objective of discussing this problem is not probability. It is what should you do if there are 2 count dimensions. Can Alien's trick still work? That's the main objective. If you're bad at probability, first learn probability, then come back to this and you would understand it. What am I saying? Independent events, etc. stuff, and all these expected value stuff also. And Pokeballs would also change. Ultra Balls would also change because you are using both of them. Okay. And you need to return maximum of throwing a Pokeball, throwing an Ultra Ball. Throwing an Ultra Ball, throwing both, and skipping. Whatever is the maximum, whatever gives you the maximum. This should be returned. Okay. So I hope this recursion is clear, and I hope you can DP this, but it won't get accepted because constraints are too high. Constraints are n equal to 2000 and A, B are also nearly the same. A and B are also nearly the same. So it's 1000 into 1000 into 1000. So it's 10 power 9. It won't get accepted. So we have to eliminate the 2 states, both of them. Okay, we have to eliminate both of them. So since we are getting late, I would show you how to do it when there are 2 dimensions using my submission. which got accepted. Okay, so when there are two stuff, how to handle that? First thing, we have a obvious stuff that is not better. Okay, I guess I should be writing the code. Isn't it? Don't you think I should be writing the code? Okay, anyways, since I've opened it, I would explain from here only. Once again, we have written the same thing. I would be explaining it very clearly. We have the same stuff, node better. So to compare two long doubles or any floating point values, perhaps you cannot compare them like directly the way you compare integers, because they don't really get equal, they converge. There's a difference between getting equal and converging. So if the difference is greater than epsilon, that means they are not equal. And if the difference is less than some epsilon, EPS, their difference is like less than some, how do I say, is, in integers you can basically do this. A equal to B. But in case of some doubles, you shouldn't be doing this. You should be checking for convergence. Like, are they getting really close? So if their A minus B value is less than 10 power minus 8, or the way you write in C++ is 1e minus 8, the E notation. Okay, if it's less than this, that means they're almost equal. Okay, they're almost equal. So we are saying that if they're almost equal, then yeah, the same comparator, the tie breaking thing. If they're not almost equal and one has a greater value, other has a smaller value, the greater value would be the answer, since we are being asked the maximum possible expected number of stuff. So the greater value would be better. Next, the next thing is, that's the first thing. And if pokeballs and both pokeballs are not equal, return the one with the smallest pokeballs. And if pokeballs are also equal and this values are also equal, when I say equal, I mean they have converged, they're very close. In that case, compare the ultra balls and check for this. Okay, and again the same thing, level equal to n, return 0 0 0. We can't do anything further after this. This is the final level, and we have possibilities like skip. Okay, we have possibilities like skip, and we have node P, which is only pokeballs. We have only pokeballs. So when you're throwing only pokeballs, the probability of that pokeball would get added. And penalty for the pokeball, I've written penalty A as penalty for the pokeball. Penalty A is the penalty for the pokeball. I would remove it from this, and pokeballs count plus. Next thing is the ultra ball. Ultra ball is also recursion of level +1, and to this I would add like u dot val plus equal to the probability of that ultra ball into 1, which is the expected value, and the penalty on ultra ball would be removed, and ultra balls plus. In case of both, I would add the probability of this. Both penalties would be subtracted, both dot pokeballs plus and both dot ultra balls plus, same as this particular recursion. In this case, both of them are getting incremented, so here also we would increment them. Now coming to the interesting part. In this case, we have to do a nested binary search, because we need to find both penalties for pokeballs as well as ultra balls. Just do a nested binary search. So again the same thing, since it's double, while start is less than or equal to n for ultra balls, this is for ultra balls, and inside this there's another binary search which is for the pokeballs. Okay, so that was the thing. in case you have like two things to optimize, two count dimensions, do a nested binary search. That's the simple thing. I hope the explanation was clear, like how to write aliens trick. And if you are somewhere dangling around 1700s, maybe if you are lucky, some contest would show up where you would use this instead of some other optimization. So usually they don't give questions on aliens trick, but this particular question was supposed to be solved with convex hull. Okay, this particular thing was supposed to be solved with convex hull. Like there's also a solution which exists, which can be done with convex hull, and convex hull is quite tedious to implement unless you have the template made for it. Okay, during a contest, implementing a convex hull is absolutely ridiculous. And I'm speaking about offline contests. Like I've been part of some contests where templates are not allowed, first thing. And the second thing is, even if you have the template is too lengthy. Yeah, you won't be typing it all the way in the contest unless your typing speed is some good WPM. Mine is only somewhere around 60s. So for me, I would prefer this aliens trick. Comparatively easier to type as well, and it's not too huge. If you see, it's just couple of binary searches hardly, and this recursion is also pretty intuitive. So it's something that is more close to, like, it's implementable, right? I don't know if there exists a word implementable or not, but it's, you know what I mean. You can implement it easily if you write this particular recursion very fastly on paper. That's what I usually do. If you manage to do that, you can do the aliens trick also very easily. So I hope this is clear. Fine. Okay, so ending the recording. Thanks everyone.